This is one of those rules for differentiation. Now this time we are on complex numbers because we have here a complex number z, or I mean this is now a complex function. So we're going to show or prove that the derivative of an exponential function e to the power of z is just itself. We know this to be true, equivalent as well to the derivative, okay, of our e to the power of x with respect to x is also e to the power of x. We know this to be true in the context of real numbers. Now, we're going to show that that is also true when x is actually now a complex number. To do this, we're going to use the definition. Okay? The definition tells us that for any function f of z, in this case our e to the power of z, that would be our f of z, the derivative of that is equivalent to the limit of your f of your z plus delta z minus f of z all over delta z as delta z approaches 0. So let's show that to be true, this identity to be true, using this definition. Of course, our function is e to the power of z. So we're going to use that for this area, but this is not yet known. Allow me to use the scratch portion here. Our f of z again is e to the power of z. In short, our f of z plus delta z is equivalent to e, where this becomes z plus delta z. Okay, so this is what we're going to apply here. So we're going to continue that one. By the way, the reason for this is we're going to simplify our limit, because as this approaches 0, that will be undefined. We need to make some applicable operations in order for us to this to be simplified later on, probably in some function or context, or even cancelled. As long as we can do all of those correctly and find the equivalent form that would hopefully arrive at this value or function. This is equivalent to the limit. Our f of z plus delta z is this one here. So you have e to the power of z plus delta z plus your original function e to the power of z all over delta z as delta z approaches 0. Let's manipulate our numerator. Take note that this is actually under, the exponents are actually addition in nature. So we can use here the rule for multiplication law. This could be actually equivalent to e to the power of z times e to the power of delta z. That's the reverse operation of the multiplication law, because if we're going to have the same base, you can add the exponents, right? That's why it looks like that. So similarly, we're going to apply that here. We're going to break the first term of our numerator. This is still the limit. Let me write it this first here. So this will become e to the power of z times e to the power of delta z minus e to the power of z over delta z. Again, let's continue because this is still present here. What we need to do next is to factor this one here and that, because they are both found on the two terms of your numerator. So when you're going to factor that, this is what will happen here. The limit of e to the power of z times what remains in the first term as we remove that is e to the power of delta z minus, as we take that out by factoring, we still have 1 at this portion, still over delta z as delta z approaches 0. Now, look into this one. This is already considered as another form, and since another function, even constant, because it's the delta c that will approach 0. So you can of course take that out as a constant, treating that as a constant, just like the limit, the rules on limit or limit theorems. But let's just stick to that in the meantime if you would like to, because you will have it here. You can break the two. You will have e to the power of z and only share this to the binomial expression here. So you have times e to the power of delta z minus 1, sorry, it's an exponent, minus 1 all over delta z as delta z approaches 0. Okay? Since both of them are just numerator, just like if we're going to have 5x over x, this is equivalent to 5 times x over x, right? You can share the denominator on one of the terms if you would like to. Okay, so that you can cancel that and so on and so forth. This time, we shared it to this expression because we have a concept for that in our calculus. Now, applying the rules of your limit, you can share this to both of them. Okay, the limit of a product is equivalent to the product of the limits, e to the power of z, sorry, that's delta z minus 1 over delta z as delta z approaches 0. Of course, as mentioned, this has no delta z, so it will be taken as a constant in itself, times. Here comes the concept. What is this equivalent to? Now, if you can still remember in our calculus, we do have this specific example or identity. We have e to the power of x minus 1 over x as x approaches 0. This is actually an identity with an exact value, because if we're going to use x here, that's 1, because any expression with exponent of 0 is 1. 1 minus 1, 0 over 0, indeterminate form. Right? We can cancel that, right? Indeterminate form. But in calculus, this is actually an identity equivalent to 1. Okay? We have a video for this on our calculus playlist in this channel explaining this to be true. So I'm going to place the link on our description at the bottom so that you will also be able to review this specific identity. Because that is true to be equal to 1, you can simply return it here. You will have e to the power of z times 1. Hence, you have e to the power of z. This shows that the derivative, okay, of our e to the power of z function using a definition, okay, is just itself. Hence, the derivative of e to the power of z with respect to z is itself e to the power of z. We have shown this to be true using the definition and this very important concept in our calculus. Again, a link for the video explaining that in the context of real numbers in the calculus will also be placed in our description for you to be able to be guided on this specific equivalence. But this shows this identity to be true. Thank you very much for watching.